بسم الله الرحمن الرحيم. الحمد لله والصلاة والسلام على رسول الله نبينا محمد وعلى آله وصحبه وسلم. السلام عليكم ورحمة الله وبركاته. صبحكم الله بالخير يا شباب.
صباحك الله من نور.
طيب, today we will start talking about a new subject, which is Laplace Transform. Please put your ID number on the chat. I think I'm sharing my screen right now with you. Can you see the screen now?
Yes.
Okay, so today we're going to talk about the Laplace transform, and inshallah we will go through this Laplace transform. First of all, we will compare the Laplace transform with the Fourier transform. Then we will define the Laplace transform in the forward direction and inverse direction. Then we will cover the region of convergence, ROC. And we will see there are many similarities between the Laplace transform and the Fourier transform. In the textbook that we're taking for this course, the Laplace transforms comes a little bit in the later stage in the textbook, and as we mentioned last meeting or last class, see the Laplace transform comes in section number 9, chapter number 9. So we're jumping a little bit more chapters. So number 5, number 7, we're not considering it. We just jump to Laplace transform. Then after the Laplace transform, we will go back to sampling and then discrete Fourier transform. So the reason why we're jumping to Laplace transform, because we want to finish from continuous time systems and signals. Once we get all this together, then we will go to the discrete time, and the introduction to the discrete time will be through sampling. And if you look at some other textbooks, you will find that the order is different than what is shown here in this textbook. And this order that I'm following, it does make sense in many different textbooks. Okay. Talking about the comparison between Laplace transform and Fourier transform. As we have seen, the continuous time Fourier transform, the CTFT, I'm usually summarize it on FT, Fourier transform, but you will see it a lot that this is called TTFT, continuous time Fourier transform. And the definition of the continuous time Laplace Fourier transform is shown here. So this is the synthesis equation.
Doctor, I think you're not sharing the PowerPoint.
Okay. We try again. What about now?
Yeah,
It's now clear.
Okay. So this is the definition of the continuous time Fourier transform, the FT. So as you can see here, there is two equations, one to go to the frequency domain, and this is the analysis equation, where we get the time domain as an input and the frequency domain as an output. And we use the exponential, the imaginary complex exponential part here to move from time domain to frequency domain. And the reason why we have used this, because this constitutes an excellent eigenvalues or eigenfunctions for our signals. So whenever we got this exponential, we will be able to move from time domain to frequency domain. And if we flip the sign here and we use the same term, we will use it to reverse back from frequency domain to time domain, as we have seen in the synthesis equation. So this is what we have seen as a Fourier transform. We want to compare this, or again, this is as a notation. What we can do here is that this is if we do have this as an eigenfunction, we could multiply it by this impulse. So if we put this as an input to the system, the output of the system will be just an h of t. So this is why we used the exponential functions as our mean to move from time domain to frequency domain. Now, if we want to generalize this concept from purely imaginary eigenfunction or purely imaginary exponential function, this one here, the exponent, it is a purely imaginary, right? معايا شباب? So if we look here, this is a purely imaginary function. So j omega t is a purely imaginary function. If we want to generalize this as a general complex, we have to add some real. This is imaginary, so we have to add some real part over here. And doing so, we will move to what we call it the S variable. So the S variable is again the j omega plus the sigma function, which is here. So if we define our exponent to be S, and the S is defined as a two component of a complex number, real and imaginary part, then we have defined our Laplace transform. So we use this S as the exponent term times t to move from time domain to frequency domain. So if we put this as an input to our system, we know that we can use a convolution equation with the h of t as given here. So e raised to power st, and s is the complex numbers given by this equation. Then we could we could calculate the output using the convolution equation. As we know that if we have an input here, this is x of t, and this is h of t, and this is y of t. So y of t would be equal to the convolution between x of t and h of t. And if we substitute the equation of the convolution, we will get this result. So it is the integration from minus infinity to plus infinity of h of tau times x of t minus tau. And x of t is given by this equation. If you substitute t minus tau in this equation, you will get e raised to power s t minus tau, then d tau. Now, if we look close enough into this point, then we would see again that we can split this exponential to be e raised to power s times t times e raised to power minus s tau. So we could split this summation into two parts. This is the first part here, and this is the second part here. And once we split them, this is independent of tau, we could move this exponential outside the integration. And once we move it outside the integration, we will get to the same result as we've seen here, that there will be an eigenfunction which we can separate them from the function itself. Doing so, then we could get this as an h of s, and this will be a multiplication factor of it. So this will be just this multiplication factor, and this is what we call it capital H of s. And then we define the h of s as an impulse function times this e raised to power minus s of t if we brought this back into the integration. So this is again the similar manner. If we generalize the exponent from a purely, let me just remove this t, from a purely imaginary part to a complete complex exponential, then we will move from Fourier transform of j omega to the s complex, completely complex exponent, which is sigma plus j omega, and we will get to the same result. So this is the definition of the Laplace transform. As you can see here, from here, this is the definition of the Laplace transform, and if we put it in terms of x of t, then we will be able to find the synthesis, the analysis equation from this function. So it will be capital X of s, it's not j omega anymore, so capital X of s will be the integration from minus infinity to plus infinity of small x of t times exponential of minus s t dt. So the main difference here is just replacing the j omega with s, and here we replace it j omega with s. So what we did is that just we will let s is equal to sigma plus j omega, and simply we add this real part in our factor. And this is the definition of our Laplace transform and how we did move from time domain to the what we call it here S domain. It's not a frequency domain anymore. This is, we call it S domain. So this is again a mapping to a Fourier transform, and here to Laplace transform. It's just a mapping from time domain to another domain, at which we could get some more data or analyze the signal from different perspectives. And here we are comparing the two domains from Fourier transform and S transform, and as you can see, we just switched from omega to S, and here we changed from j omega to S, and as we know that S is again j omega plus this real part. في أحد عنده سؤال الآن على الموضوع هذا؟ فقط ال generalization we just add this real component.
دكتور ليش بنضيف الريل بارت؟ يعني ليش اضطروا انهم يسووا زي كذا، او ليش موجود ذا الشيء؟
هو السؤال يعني دائما في mathematical models they want to make it more general and they will see how they will implement this. لأنه بعض الأحيان there will be some systems which when we solve it out we will get to a point where there will be a generic form, not only purely imaginary. So in that way they cannot fit it in Fourier transform. They need to see a more generic form. That's why they generalize it from purely imaginary to more generic, which is a complex exponential. Sometimes they will be طبعا when you work with Laplace transform compared to the Fourier transform, you will feel much easier to work with the Fourier Laplace transform. Since it is just an S, one letter, compared to the J omega, which you feel you will work with a little bit more component. لما حتشوف انت في ما ادري شوي طبعا لما حنشوف نحن كيف حنستخدم الاس وحتسهل لنا اشياء كثيره داخل السبستيوشنز في حتى مثلا لما ناخذ الكتريكال سيركتس حنشوف لما نستخدم الفورير ترانسفورم نحن استخدمناها من قبل، ولما تشوف الآن تستخدم الاس domain you will find that the S domain is much easier because you will be capable to use not only purely imaginary also the real part. لما تجي تعوض عن يعني element بالمعادلات حقتها، يعني كل element له رمز يعادله في الاس دومين او في الفورير ترانسفورم دومين. فلو استخدمت الفورير ترانسفورم حتشوف انه الامور شويه تتعقد اكثر، لكن لما تستخدم الاس دومين بتكون اسهل واكثر سهوله في التعامل معها لانها a complete complex number, not just the imaginary part of the complex number. وممكن أبحث زيادة في الجواب، وإذا في أحد من الزملاء حصل إجابة أكثر من كذا يعني وأرجع لك يوسف على الموضوع.
تمام دكتور.
طيب now we have this new variable which is called s, and this new variable is constitute of this sigma plus j omega as a complex number. And if we want to go back to the Fourier transform, so this is the Fourier transform simple. If we want to go to the Fourier transform, we just simply let this sigma equal to 0, and we will get back to our Fourier transform. So S will be equal j omega, as you can see here. And once S is equal j omega, we will go back from Laplace transform to the Fourier transform, and this is equal to this. طيب طيب this is another reason. Maybe it will give you some insights about why we need to generalize it from Fourier transform to a Laplace transform. Why do we need to generalize it using this, adding this component sigma as a real part? So if we look here, the x of s would be equal to the Fourier transform of x of t times this real component. This is purely real, right? So if we follow this derivation, you will find that the Laplace transform will be equal to the Fourier transform of the signal times this real part. So if we get some signal of t, and if we multiply it by this factor, which is e raised to power minus sigma t, then if we take the Laplace, if we take the Fourier transform of this, both of them, then we will get to the Laplace transform. So when we use this component, as you know, x of t is not always we can find the Fourier transform. There is a condition that x of t would converge. And the reason or the condition is that that we can get the integration of x of t for all the value from minus infinity to plus infinity. So if this was not finite, the area under the curve was not finite for x of t, then this would not converge and we would not be able to calculate the Fourier transform. So if we add this component, e raised to power minus sigma t, this component would add an effect from one side, as you will see here. From one side, this is the if we get this as a positive number, so this will be the plot for e raised to for the exponential factor. So if we multiply it by this factor, then it will push it from, if we divide this plot into two parts, it will push it down from this side and it will push it up from this side. And as we can see, there are some certain functions. If at left side it was equal to 0, then it will help to if it is from one side it was equal to 0, so this would help to push the function towards the x axis and make it even converge. So the Laplace transform may converge when Fourier transform does not converge. So this might help you also. So there are some functions which does not exist in Fourier transform. You cannot find out the Fourier transform for it because it does not converge. When you generalize to S domain, you may be able to calculate the Laplace transform for it, while you are not able or capable to find the Fourier transform for it. And this does make sense. Why should we move from Fourier transform and to Laplace transform? Do you get this point?
Yes.
Now let's recall the complex exponential functions as we have seen. This is the complex exponential functions, and we do have different types of complex exponential functions. And if we have defined the s as given here, s is equal uh, sigma plus j omega, then we would draw this complex domain, and this is called S domain. So if both of them was positive, then the exponential, so the sigma is positive and omega is positive. So this is the real part, and this is the imaginary part. So if both were positive, then this exponential will be plotted in this way. And if we have a negative real part and a positive imaginary part, the exponential will look like this plot here. And if both were negative, then we will get this decaying function. Now, this is when we talk about purely real function. So this is real. Sorry, this function we have omega is equal to 0 and a positive sigma, and here omega is equal to 0 and negative sigma. Okay, and if we do have negative part of sigma, so this is sigma is negative, and whether it is positive or negative omega, it doesn't matter, it will look like this function here. And if we do have a 0 omega, sorry, a 0 sigma, then we will have this type of functions. So as we can see, when we do have 0 omega, we will have purely real as shown here and here. This is purely real, whether it is increasing or decreasing, exponentially increasing or exponentially decreasing. This is the first part. Second part, if we had negative sigma, and it doesn't matter whether it is in positive or negative omega, it will be decaying in this way. And once we approach to the 0 omega, we will have this fluctuating like a sine wave or cosine wave, and this is not anymore a stable system. This is, we'll call it marginally stable. And once we got into the positive sigma, whether it is in the top side or negative side, it will be for sure unstable system. So if we want to compare this with the Fourier transform, for the Fourier transform, we are limited to sigma equal to 0. And where is the sigma equal to 0 in this line? Is just this vertical axis. So when we talk about Fourier transform, we were talking about only this line. Once we add this sigma, then we have switch from this axis to this plane, as you can see here. And as you can understand, we prefer to stay on the left side of this domain, S domain. So whenever we are at the left side of this S domain, then it will be, this exponential will be somehow stable. Right. I will leave this for you to read it at your time. Okay. Now, this is an original problem. Will explain to you again and again why do we need to move to Laplace transform or Fourier transform. So in the original problem, if you try to solve it immediately at the time domain, you will get a difficult solution like differential equations. Then you will get to the solution of the problem. And you have to go with this very difficult path, which takes a lot of time and energy to solve. And sometimes you would not be able to solve it. The other alternative is to go through a transformation, go from the time domain to another domain, which makes the problem a little bit more easier. So the problem in this transform phase, you can follow relatively easy solution to go from this space problem to the solution of this space of this problem, but in a different space. Then you have to get back to the original time domain through this inverse transform. So you have to go back to this inverse transform. So as if there is a line here, and we're moving from our world, like let's say time domain, to a different domain, and then solve the problem there, and then come back to our time domain. So we're doing all this just to avoid the difficult solution. And this is the Laplace transform. I don't want you to bother yourself about these transformations. Right. In the Fourier transform, we're transforming from t, which belongs to the real number, into omega, which belongs to, again, a real number. In the Laplace transform, we're transforming from the t, which is belong to the real number, into the s, which belongs to the complex domain. Effectively, operation in complex can be partially considered as operation in R2. This is meaning that we have two axes, which is the omega and sigma. This is called R squared. So we have this real axis and we have this real axis. This would require further knowledge about handling the integration complex variable functions in complex domain. Thus, some mathematical Roger will be escaped, unfortunately. But again, this S domain came to us. So as you can know, both of these variables are positive at the first quarter. At the second quarter, the sigma will be negative and omega will be positive. At the third quarter, both of them will be negative. At the fourth quarter, sigma will be positive and omega will be negative. Now we will come to know what we call it bilateral and unilateral in a moment. So the bilateral is the function that goes from minus infinity to plus infinity. The unilateral is a function goes from one side only, so from 0 to infinity. We will see that also sometimes it will go from minus infinity to 0. So the bilateral is a function that we're defining the function from minus infinity to plus infinity. So this is the bilateral. But the unilateral, it will be either from 0, then it will go to infinity, it will be defined, or it will be the otherwise from here, and then it will be defined only. This will be almost 0. And as you can understand, why do we need to differentiate between these two? Because at the end, we're going to multiply by this factor, which is e raised to power minus sigma t, and this would be effective to work on one region to make it more stable compared if it is from the other side. And we will see that there will be some different tables for this bilaterals and unilaterals. Okay, so this is again the definition of the Laplace transform, and this is from bilateral side. And this is the inverse of the Fourier, inverse of Laplace transform. So both are Laplace transform. This is the forward direction, this is the inverse direction. I would skip this discontinuity. Okay, now I would move to some Laplace transform of some examples of Laplace transform, but I would prefer to have a break. رايكم شباب ناخذ بريك مدة 5 دقائق. السلام عليكم ورحمة الله وبركاته.
وعليكم السلام.
طيب شباب خلينا ناخذ الاتندنس. طيب مين اللي موجود معانا؟ محمد الزباني. موجود محمد؟ محمد موجود محمد؟ طيب تركي الشريف موجود تركي. عبد الله الرشيدي. عبد الله الرشيدي موجود. طيب محمد الجهني.
ايه يا دكتور موجود.
أديب الرفاعي. عبد الرحمن الغامدي.
حاضر.
ويوسف الشهابي
يس.
موجود، ومحمد الجحيف. محمد موجود؟ محمد إبراهيم موجود. أحمد باقاسي موجود. أحمد
حاضر.
وطاهر موجود.
موجود.
طب عندنا واحد ناسي. طب اللي ما هو موجود محمد الزباني، عبد الله الرشيدي، وأديب الرفاعي، محمد الجحيف، وإبراهيم الجحيف. طيب نكمل. So this is the example that we could do a Laplace transform for the unit step function. So if we substitute in the equation, and we will see inshallah, we will get the unit step function is replaced by this 1 over s. You see, this is much more simpler to the notation that we could 1 over j omega. Even working with this expression and this expression would be much easier to compare this with that. كيف معي يوسف؟
يس دكتور.
And if we want to go for the exponential, you will find out that the Laplace transform of the exponential, this purely real number, or even if you want to complex number, then it will be 1 over s plus a. So let's do these integrations. So an exponential, which is times u of t, this is bilateral or unilateral. What do you think?
Unilateral.
So this is unilateral, so it goes only from one side. So unilateral, it goes only from one side. Bilateral, it goes from both sides. So this is a unilateral, and when we want to find out what is the Fourier transform for it, we will find that this is the Fourier transform of this function, and this is for a greater than 0. So if a is greater than 0, then we will be able to find this exponential. Now, if we compare it with the Fourier transform, then we will replace this with this. So it is very comparable, even if you move from time domain to frequency domain in Fourier transform, or you move from time domain to S domain in Laplace transform, you can still, if you use to the Fourier transform, then you can find out the Laplace transform much easier now, because you're used to the Fourier transform. And now, as you can see, that it's not only A which controls the convergence, but we add plus this, we add plus sigma. So A plus sigma should be equal to greater than 0. And if you do the calculation, you will find that sigma is greater than minus A. So in other words, you can say that the real part S is greater than minus A. And in that manner, this is why it is generalized. So it is not only restricted to the value of the function. يعني إذا أعطاك الفانكشن في البداية A equal كذا خلاص you cannot control it. It's only converging at this moment. No, here you can start controlling this through through the S domain, where a region, a bigger region of convergence, you can work with this function. So as you can see, the Laplace transform goes to a similar transform to the Fourier transform, replacing j omega with S, but the region of convergence which makes a big difference to us. Now, another example, what about if we get this function? And this function compared to this function is just, we are switching the t. So we're switching from okay, we're switching from u of t to have u of minus, and the other change is that we put a negative sign. So now just do not focus on this negative side. Let's focus on this negative. What is the effect of this negative sign on this function?
It will flip the signal.
Yeah. So if the signal was this is the exponential, and in the beginning we multiply it by let me use another color. So in the beginning we use to work تغير كل اللون، نضيف لون ثاني طيب. So in the beginning we were focusing on this side, so we use this side in the beginning. Now we will be focusing on this side. Okay, so the result of the first function was, this is the 0 position, it was this function. Now the result of the second function, it will be this function. You see? So whether we are multiplying in the positive side or in the negative side, we will see. But this is, we did not multiply by minus sign. So if we multiply by minus sign, this will be flipped down side. So it will be somehow this shape. Now even this is increasingly going up, but still we could find a region of convergence, because if we multiply it by another factor of exponential, and that exponential where the real part were negative, the real part on S domain is even less than this minus a, then it will be this sigma minus or plus a. Since this is greater than a, the entire thing will be less than 0, so negative. Even this goes crazy here in the time domain, but we could find a way where we can make it convergent using this sigma part. So if you compare both results, this result of this example with this result of this example, you will find the result is the same, right? So two different functions come to the same Laplace transform. Does this make sense? هل هذا شيء معقول؟ يعني في time domain is different function. So this is a different function than this. You look at this. This is the first function. This is f1, and this is the second function, f2. It's totally a different functions, right? But at Laplace transform, both comes to the same result. So this is 1 over s plus a, and here is 1 over s plus a. هل هذا منطقي؟ هل هذا ممكن؟ In the Laplace transform, yes, it is possible. And the main difference is that the region of convergence is different. So the region of convergence here is the real part of S is greater than minus A, and here the region of convergence, the real part of S is less than minus A. Here is greater than, here is less than. So the region of convergence, the ROC is very, very important here in the Laplace transform. So in Laplace transform, the region of convergence is very, very important. Now, let's take another example, example number 3. So if we take this example, which is e raised to power minus t times u of t. Now, a here is equal to what? 1. And here is e raised to power minus 2t times u of t. And a here, this is a1 will be equal to 1, and a2 will be equal كم يا شباب؟ 2. So using this table, so we have this function, so e raised to power minus a t u of t, we will get 1 over s plus a, and the real part should be greater than minus a. So I can use it and find out the Laplace transform of the first part. So this will be 1 over what? S plus a, and a is equal to 1. And this is plus, second one is 1 over s plus 2.
1 over s plus 2.
1 over s plus 1, this is the first one, and this is for the second one, 1 plus s2. Okay? So the Laplace transform of the first one is this, and the Laplace transform of the second one is this. Now, the question is, which region of convergence should we get? So the region of convergence for the first one, we should write real of S is greater than minus A. صح؟ هذا اللي كانت معنا هنا. Region of S is greater than minus A. This is the first one. And here, the region of convergence is given by real part of S is greater than minus 2. فعندنا two region of convergence. Which one should we get for the entire solution? Let's draw the S domain. So this is sigma, and this is omega. So the real part of S is this, right? This is the real part. So when we said the real part should be greater than minus 1, so this is minus 1. So for the first region, it is this part, greater than minus 1, this right side. Now, for the second one, we're saying that real part, this is sigma and this is omega. So real part of minus 2 this is minus 1. So real part of minus 2. So this is the real part should be greater than minus 2. So in some sort of that 1 over s is convergible or is solvable on this region, and 1 over s plus 2 is solvable on this region. So the summation of both of them, we should get both of them. So this region and this region will exclude this small part, because at this small part it's only convergible for 1 over s 1 over s plus 2, but it is not converging for 1 over s plus 1. So we will exclude this, and the entire solution will be r. The real part of s is greater than minus 1. So this will be our. So again, we have to take the convergence at which all the terms are converging. So if we find the solution for the first part to be at this side, then the second part will be at this side. So we will take the intersection between both areas. So the intersection between both areas is after minus 1 to infinity.
دكتور
تفضل
دكتور
تفضل.
yes I didn't understand why we did we discard the function
دقيقة
before minus 1. okay
تسمع صوتك؟ معلوم كيف ماني قادر اسمع الصوت. تفضل.
yes did you discard the function before minus 1 in S domain? Or what do you mean by the solution is for minus 1 conversion?
When we solve this function, we get this solution. So this is the function, and this is the solution. 1 over s plus a for real part of s greater than minus a. At this region only it will converge.
Okay.
Otherwise it will not exist. This is not the right solution. There will be no solution. طيب.
Okay.
فأخذنا مثالين، هذا المثال الأول وهذا المثال الثاني. لما تحل المثالين تطلع نفس الريزلت 1 over s plus a 1 over s plus a a function at the symbolic function at Laplace transform exactly the same. What is the difference is only the region of convergence. هذه الفانكشن it will converge on greater than minus a, and this function it will converge in less than minus a. ف two different functions، هذه الفانكشن الأولى وهذه الفانكشن الثانية مختلفين في التايم دومين تماما، تعطيك نفس السولوشن في اللابلاس ترانسفورم، والفرق فقط في الريجن of convergence. طيب؟
Okay.
Now, whenever you get the solution, you have to define the region of convergence. So when we try to solve this fits where? Is it this function or is it this function? It is f1,
This
right?
function.
It is the first function. So we use a solution with this region of convergence. So we use the same solution with this region of convergence. It should be greater than minus a. As you can see here, greater than minus a. So it will converge هذه الفانكشن. We can find the solution. نقدر نوجد الحل فقط في المنطقة هذه. And this one we did the same. It converged only in this region. طيب الآن عندنا summation of two terms. واحد converge في هذا الريجن وواحد converge في هذا الريجن. لما نرسمها في الاس plane, this is the S plane. when we plot it in S-plane, we will find this is the area for the first term, and this is the area for second term.
Yes.
But there is an area, this one, it applies only for the second term, but not for the first term. But if we look after -1, both is converging. So that's why we will take the intersection. يعني لو شفت التقاطع بين two areas, it will be defined by greater than -1. Right?
Yes.
So we have to take this and this, but take an intersection between them. That's why we decide to go with greater than -1. طيب الآن we can add these together. طبعا لو سوينا summation between them نضرب s plus 2 هنا على المقام حيصير s plus 1 times s plus 2 نوحد المقامات طبعا وهنا نضرب في s plus 1. So if we sum the denominators we will get 2s plus 3 over s plus 1 times s plus 2 وهذا هو السولوشن الموجود قدامكم. Is that okay?
Yes.
Right. Let's move. Now this is again what we have discussed. So now to know this is now just to make it لما تشتغل انت مع Laplace Transform النقطة الجديدة عن الفورير ترانسفورم is the region of convergence. يعني التعامل مع التيبلز become much easier. Now ايش الإضافة الجديدة عن الفورير ترانسفورم؟ كل شيء قاعد يتكرر معنا نفس اللي شفناه في الفورير ترانسفورم قاعد يجي مع لابلاس ترانسفورم. الإضافة المهمة الجديدة اللي لازم نتعلمها ونفهم كيف نتعامل معها اللي هي region of convergence. والregion of convergence الاس دومين الآن نحن بنعطيكم بعض القوانين اللي بتساعدك في التعامل مع هذه region of convergence. طبعا when you do have like a function in this shape you have to give the nominators and denominators. Give me the zeros and the poles. The poles is when the d, this is d of s over n of s. So the nominators and denominators. So when n of s is equal to 0, we call it the zeros. And when d of s is equal to 0, this is we call it poles. And zeros we are giving it the symbol of circle, and the poles we're giving it as the symbol of x. Like if we try to solve the nominators, so 2s plus 3 is equal to 0, meaning this one. And s equal to what? Minus 3 over 2, which is 1.5. Minus 1. So this is the zeros. So I have to go, and this is real, huh? I have to go on the S domain and put this circle. So this is minus 1.5. And then I will solve the denominator. So ds will be equal to s plus 1 times s plus 2. And this will be equal to 0. And this will give us s is either 1, minus 1 or minus 2. And these are the poles. So we will put the x here and here. So there are some rules for defining this region of convergence. The first rule region of convergence will be like strips. الستريب اللي هو زي الأعمدة من فوق إلى تحت. طبعا if it is converging for one certain omega, so omega is equal to 0, it will be converge for all different values of omega. فمن minus infinity to plus infinity كلها هذه حتكون معنا. If it is converging also from another value of omega, so it will be converging from all different values of omega. So that's why it will be vertical strips. So I would write vertical. From minus infinity to plus infinity. This is, we're talking about imaginary part. Now, second point is that it has to be connected. ما تقدر تكون two strips not connected. It has to be connected. يعني ما ينفع يكون عندنا strip هنا strip هنا. No, it has to be connected. طيب, third one, we cannot have a pole in one of our region of convergence. يعني هذه قوانين ثلاثة دائما صحيحة. فداخل الريجن ما تقدر تحصل هنا بول. البولز لازم تكون outside الريجن of convergence. لأنه بمجرد ما تكون البول طبعا على الحد ما عندي مشكلة، طبعا تكون منقطة لأنها not included. إذا حطيت خط يعني أنها included، لازم تكون منقطة لأنه هذا البول من minus infinity to plus infinity, this is marginally stable and we should not include this. We should just put this dotted line. لما تحط خط متقطع يعني انه هذا not included، لكن ما بعده included. طيب, let's see. So it will be one region connected، يعني مثلا يا هذه المنطقة يا هذه المنطقة اللي بين الاثنين يا هذه المنطقة اللي موجودة هنا. بس ما حتقدر تقول والله هذه المنطقة وهذه المنطقة، لا. ولازم تكون vertical strip من minus infinity to plus infinity. ما ينفع تقول والله هذه المنطقة اللي فوق ما هي معانا، لا، كاملة من minus infinity to plus infinity. وتكون ما في داخلها واحد من الحين حنشوف بعض الاكزامبلز وكيف نتعامل معها. طب this is again, this is the denominators and this is the denominator, and this is, we call it zeros of x of s, this is poles of x. So again, these are the poles when we put ds equal to 0, and region of convergence for x consists of a strip parallel to the j omega axis, the s-plane, and the Fourier transform of x of t converges, then ROC includes the j omega of axis in the s-plane. So if the Fourier transform converge, then also the axis j omega, this axis will be included. شايف هذا الأكسس will be included within the region. طيب, now let's consider some generic examples. If we do have a function that is finite duration, what does it mean, finite duration? Meaning that in after a time t1, before time t1, or after time t2, the function will be equal to 0. It is defined only in this period, from t1 to t2. Within this period, it is defined. Otherwise, it will be equal to 0. So this is finite solution. If you do have this and you multiply it by a decaying exponential, and this function is defined, is not going to infinity, is defined between this duration, then the region of convergence will be the entire S-plane. So this S-plane, this is real, and this is imaginary. The entire S-plane is our region of convergence. From minus infinity to plus infinity, from minus infinity to plus. And the reason here is clear, that we can find out what is the entire region here under the area, under this function. And if we multiply it by this decaying exponential, we will push it further down. So we will be able to find out what is this function. طيب. And we can do it both sides, whether it is decaying exponential or growing exponential, both. One side we will push it down, and the other side we will push it up, but at the end it will be a finite number, and we could calculate the entire area under this function. Right. This is what we call it finite duration. Now, the next type is the right-sided function. So the right-sided is that it is defined after t1 a certain time and the time axis. So before t1 it will be equal to 0, and once it reaches to t1 it will be defined all the way to infinity. So this is, we call it right-sided function, because the function is divided on the right side of this t1 compared to the left-sided, which will be flipped to the other side. So the right-sided will be the real of S is equal to A0 is in ROC, and all values which real S is greater than A0 are in RO. So the region of convergence here will be greater than A0. So if you put the region of convergence, then this is A0, for instance, then you will have greater than A, all this area will be our region of convergence. So this is the right-sided, and x of S rational, then ROC. Now we're only talking about x of S is rational, polynomial in this shape. Okay. Then ROC is in the right of rightmost pole. فلما نحلل denominators والdenominators ونبدأ نشتغل عليها، فنجي نقول حيطلع معانا ds equal to 0, and this is will give you the poles P1, P2, and etc. Then the region of convergence will be to the right of the rightmost pole. فلما نحط البولز هنا على ال S domain, فرضا this is P1 and this is P2 and here is P3. So what is the rightmost? This is the rightmost pole. فحتكون this is the region of convergence. على يمين آخر pole في اليمين. هذا region of convergence. Is this clear يا شباب؟
Yes.
طيب. So this is the x of t is right-sided, and the real part of S is equal to sigma naught is in ROC. All values of this which is greater than sigma naught r in the ROC. And you can see that even if you give different type of exponential, whenever you exceed this value, you will be able to converge the function. The more you increase it to the rightmost, then you will decay it a little bit faster, in a faster rate, then you will be able to find the convergence. Okay. Now, even though there are some functions in the Fourier transform that the area here is infinite, so you cannot find out the Fourier transform for this region, but using this Laplace transform and using this factor, when we multiply it, then you will be able to control the area under this curve and make sure that if ft is not exist, then you can find the LT, the Laplace transform. هل هذا جاوب سؤالك يا يوسف اللي في البداية سألته؟
ما أشوف العلاقة، يعني ما فهمت صراحة زي الناس.
يعني أنت سألت ليه نحن ننتقل من الفورير ترانسفورم للابلاس ترانسفورم. واحد من الأسباب إنه في functions في التايم دومين لو حاولت تحسب لها الفورير ترانسفورم بيكون unconverged، يعني is not converging، فما حتقدر تحسب الفورير ترانسفورم، it doesn't exist. فتبغى تسوي لها analysis في الفريكونسي دومين you cannot، لأنه ال area under the curve here is infinite. يعني هذه لو حسبت لها ال area under the curve رايحة إلى infinity وهي معرفة، وممكن تكون ال area هنا almost infinite. أوكي؟ لو ضربت هذه الفانكشن في ال a raised to power، طبعا إيش الفرق بين Laplace transform وال Fourier transform is this factor. We are multiplying by this factor. So we multiply x of t times this factor. هذا الفاكتور إذا حددت السيجما هنا بطريقة صحيحة، ممكن حتى لو كان الاريا هنا كانت infinite، بهذا الفاكتور you can push it down. You can push this down to the point where you can find a finite area. تقدر تحسب الfinite area هنا. But at that moment you will be able to find the Laplace.
Okay, doctor, but what about the leftover area that we did not include?
لا، الآن أنت أفترض إنه هذه هي الفانكشن في التايم دومين. يعني في لحظة من اللحظات سويت سويتش أون، فالآن الليفت أصلا زيرو قبل، لما سويت سويتش أون بدأت الفانكشن معك، which normally does make sense. Most of the functions will be equal to zero till you switch it on, then it will become active.
Yes.
But in that scenario, this function, you cannot find out what is the Fourier transform for it, but you can find what is the Laplace transform. Okay?
Yep. Yeah.
So this is one part of why do we need to move from Fourier transform to Laplace. Right. Now, for the left-sided function, we will switch from greater than to less than. And the left-sided function, and x of s is rational, ROC to the left of the leftmost pole. So if we do have this S-plane and we put P1, P2, P3, this would be first pole, second pole, third pole, then where is the leftmost pole? This is the leftmost pole, آخر pole على اليسار, but it will be to the left of the leftmost pole. This is the region of convergence. compared to here. This is the first pole, second pole, and third pole. It will be to the right of the rightmost pole, so this is the region of convergence. فلو تشوفوا لما جينا هنا في اللابلاس ترانسفورم تركنا الترانسفورم لأن نحن متعودين عليه خلاص. أنا ما عاد جلست أشرح في اللابلاس ترانسفورم في التيبل والشغلات هذه، وانتقلنا إلى region of convergence because this is the new concept that you have to focus on. I'm assuming that you are capable enough to work with these tables to use whatever things that you want to see. We will see the table in next lecture, inshallah. Like, I just want to focus right here about the region of convergence, and it is the most important, one of the most important things that you have to consider while you are picking the solutions. Not only defining what is the numerical aspect of that function, like it is s plus 1 or s minus 1 alone, but also the region of convergence that you have to specify. Right. So this is for the first example. This is the region of convergence at the right side of the rightmost pole. And if you compare each component, there is different area of region of convergence, but you have to take both of them and then and then consider that the region that both intersect, and you will get only this region which is converging. I think if you go through this example, this is an example where you can get some more details about it. I will leave this example for you to go through.
Doctor, I have a question.
Further.
How can we know that if the function is right-sided or left-sided?
Okay, so let's look at this function. This is at time domain, right? So what do you think? This is right-sided or left-sided?
Right-sided.
This is right-sided. Immediately from the time domain, you will find out whether it is right-sided or left-sided. And what about now? I don't have a figure for left-sided. This is only for right-sided. But left-sided will be flipped. تكون بهذا الشكل.
I mean, in the if equation is given as before.
Okay, so this is the equation which was given before. What do you think? This is right-sided or left-sided?
Right-sided. Okay, I
This is
understand.
the right-sided. What about this one? Is it right-sided or left-sided?
Left-sided.
Is it clear now?
Yeah.
So you will be able to find whether it is right-sided and left-sided. If it is through equations, it will be much easier because u of t will define for you whether it is left or right. If you have like a sign in front of t in a minus sign, or if it is a positive sign in front of t. طيب ما ودي اني اكثر عليكم صراحة، بس نفس الوقت طبعا this is part of this here will be like a revision. As you see, we need to work with the region of convergence in addition to the work that we did before for finding out what is the Laplace transform. So it is not only to find the numerical solution, so like this one, it's not only to find what is the value of Laplace transform, but also we have to define the region of convergence. Whenever we define the region of convergence, then we will be able to completely define the solution. فالسولوشن عندنا الحلول اللي موجودة في اللابلاس ترانسفورم فيها أمرين لازم نعرفهم. النوميريكال بارت اللي هو الفانكشن what is the function. Second is the region of convergence. At what time or what region in the S domain this numerical expression is valid. Like you can see that you can solve some of circuits, electrical circuits using Laplace transform, and there is a definition for each element. Like if you're talking about resistance, you will replace it by a certain value, and if it is inductor or capacitor, you will replace it by a certain value, and then you will do a simple calculation, and you will be able to find out that the result is moving from derivative equations, as you can see here, all the way till you get to very simple equations like you can see over here. So this is much simpler to work with than the derivative equation, as you can see in this part. Right. Again, the partial fraction will come with us, and you have to work with the partial fractions. And what I have given as an example previously was simple examples. I think there are a little bit more complex examples in partial fraction that you have to consider. Sometimes the denominator will be not only constants, it will be also some of the s, like as plus b part at the denominator, and you have to consider this into your solutions. So what I'm asking you is just to go and review the partial fraction section that I gave you in the blackboard. Again, a partial fraction, you have to review this partial fraction. Some examples you can practice. Try to practice these examples at home and try to solve, decompose this into a component of these poles. So this will be s plus something, this will be s minus or plus something, and you have to take the factorize this exponential expression into two terms. طيب أنا كده أتوقع إني أبغى نوقف هنا ونكمل إن شاء الله الحصة القادمة. Do you have any questions? طيب إذا ما عندكم أسئلة شباب ممكن نوقف.